Assalamu alaikum, dear students. We're back with another video lesson. In the previous video lesson, we were talking about harmonics. We also talked about the difference between the harmonic series for a string, right, and also harmonic series for a pipe that is open at both ends, and also the harmonic series for a pipe that is closed at one end. We've learned about the equation of each, how to find the fundamental frequency, how to find the frequency of or any harmonic for each one of these, of course, and also the wavelength of each one of those. Today, we're going to practice some questions, and also along the way, we're going to solve some Wizard questions too. So stay with us. All right, now the first thing that we have is this sample problem, because that is where we stopped last time. It says, what are the first three harmonics in a 2.45 meter long pipe that is open at both ends? That is one part of the question. And then the second part of the question says, what are the first three harmonic of this pipe? That means the length is going to be the same, Basha, but when one end is closed here. All right, so now let's solve these questions together. Basha, so the first thing that we have says, what are the first, so here's what we have, right? First three harmonic. Right, this is the length, all right, if this pipe is open at both ends. That is the first thing that we have. So now, regarding this question, good man, if it is both ends open here, that is a pipe like this, man, the frequency of any harmonic that got n times v over 2 times the length of a pipe. So the fundamental frequency that got the 1 times, we don't have to write 1 in this case, times v, which is the speed of sound in air, which is 345. Okay, divided by 2 times the length, which is 2.45. Once you do the math, of course, you'll find the answer, which is equal to what? It is equal to 70.4. Okay, 70.4 hertz. And that is the fundamental. Now, if this is the first harmonic, what about the next harmonic? It's going to be F2, which is 2 times F1, right? That is going to be 2 times 70.4. You can find the answer. It's going to be this much hertz. What about the third harmonic? All right, it's going to be F3. It is equal to 3 times fundamental. So 3 times 70.4, that is equal to this much hertz. And this is, we can say, the first three harmonic. Oops. Let's not. All right, so these are the first three harmonic for this pipe when it is when we can say both ends are open. All right, now what about the first three harmonic of this pipe when one end is closed? Now, if one end is closed, of course, things will change, right? So we can say the equation becomes n times v over 4 times the length here. So it is the same length. So the first harmonic that we're going to get, it is F1. Don't forget, the next harmonic that we get, it is F3. And then the next one after that is going to be F5. So these are the first three harmonic that we get. Do not get confused, right? So because we don't have the even harmonics here. So it is going to be 1 times the same speed of sound in air, 345, divided by 4 times the length, which is 2.45. The answer is going to be 40 point something, 35.2. Right, 35.2 hertz, and that is the first, we can say, harmonic, right? Now, what about the third harmonic, which is the one that is next, right? We can say 3 times fundamental. Do we have to do the work again? No, just 3 times F1, which is 3 times 35.2. You do the math, that is going to be this much in hertz. What about the fifth one? We can just say 5 times fundamental, which is 5 times 35.2. Is this true? You just do the math, of course, you'll find the answer in hertz, and that is the fifth harmonic. So 3 harmonics when both ends are open, 3 harmonics or when one side is closed. So pretty easy. You can do these questions without any struggle, right? As long as you understand what the question is asking for. All right, now remember we have these Wizard questions here. These the first one says, if you blow across the open end of a soda bottle and produce a tone of this much, what will be, or what will be the frequency of the next harmonic heard if you blow much harder here? All right, so this is also an interesting question here. But first of all, before you know that, of course, In order to answer this question, you need to know which case is it. Is it a string? Is it a pipe that is open at both ends, or a pipe that is open at closed at one end? Now think about soda bottle. You have to imagine that, of course, right? So we know that one end is open, that is, we can say the top part, but the bottom part is closed, right? So that is a soda bottle. So we can consider that soda bottle, it is a pipe that is closed at one end. If not, you can just think about it, any kind of drink or whatever. Obviously, one side is open, the other side is closed after you open that. All right, so now if that is the case, the fundamental, it is 270, right? So if fundamental is 270, what is the harmonic or the next harmonic that you hear? Good man, we don't have the second harmonic because it is a pipe that is open at one end. So the next one is going to be 3, right? Third harmonic, which is going to be 3 times fundamental, 3 times 270. So you just do the math and you can see which answer it is, and that'll be it, right? So what is it equal to? You just use a calculator and you can find the answer. Pretty simple. All right, the next thing says, what is the wavelength of the second harmonic, right, in a pipe that is open at both ends when the length is this much? That is easy, I believe, so you could do it yourself. All right, let's just do this one here. It says, what is the wavelength, maybe, of the second harmonic? But man, wavelength for any harmonic, it is, if it is a pipe that is closed at one end, it is equal to 4 times the length divided by n right here. So the second harmonic here, now remember, which one is the second one? That is going to be the third one here, because we don't have F2 here. We have F1 and F3. So F3 would be the second one if we go by the order. So it's going to be 4, right, times L divided by divide by 3. So you can write 4 over 3 times L. That'll be the second or the wavelength of the second harmonic for a pipe that is closed at one end. That's simple. All right, moving on to another question. It says, what are the first 3 harmonic in this much long pipe that is closed at one end? So you can find the first 2 harmonics. So you can find F1, and if it is a pipe closed at one end, that'll be F1 and F3. So just do the math and you can find the answer. All right, now we have another question here. It says what? It says, why does a pipe closed at one end have a different harmonic series than a pipe or open at an open pipe here? So in order to answer this, of course, let me draw a diagram very quickly. Okay, so if it is a pipe that is open at both ends, of course, we can see that both ends are going to be what? Both ends are going to be no antinodes, right? So this is an antinode. Here's the center is going to be a node in here. And then what if it is a pipe that is closed at one end? You can see that one end is a node and then the other end is an antinode. So do you think these 2 pipes would sound the same? No, because one of them, it is an antinode, which the particles have complete freedom to vibrate, but this is an antinode, which the particles are restricted. They're not able, or they're not free to vibrate. This is the reason why these 2 sound different. Pipe closed at one end have a different frequency series than a pipe, an open pipe. Good man, because the open end becomes an antinode, all right, while the closed end becomes a node, and this is why, right, we hear different sounds or frequencies. Now, this is another point that you need to know regarding the 5th point in the table that we said we're gonna, like last time, we said we're gonna discuss that in another point here. That is exactly this. In a vibrating string, right? Now, the difference between any 2 consecutive frequencies is going to be the fundamental. What do we mean by this? First of all, remember the harmonic series that we have for, let's say, a string here. Or it could be a pipe that is open at both ends, doesn't matter, right? That is a string. Or a pipe that is open at both ends, because in terms of equation and everything, it is the same, right? But if it is a pipe that is closed at one end, things will change. Okay, because this one side is a node, and then the other side is an antinode. Very good, man. For the frequencies that we have F1, we have F2, we have F3, and then F4. So all the frequencies, both even and odd number, right? What if I want to find the difference in between any 2 consecutive frequencies? When I say, or any 2 frequencies that come after one another. So for example, I want to find the difference between any 2 frequencies between 3 and 4, let's say. So the difference in frequencies is going to be F4 minus F3. But F4, the cut of 4 times fundamental. and then minus F3 decat, the 3 times fundamental, right? This, you take fundamental as a common factor, if not just 4 F1 minus 3 F1, that would be 1 F1. So you can see that the difference between any two consecutive frequencies, or the frequencies that come after one another in a string or a pipe that is open at both ends, will always equal to 1 times the fundamental. Basha? But if it is a pipe that is closed at one end, all right, we have F1, we have F3, we have F5 and F7, and then goes on, right? Only the odd numbers. If I want to find the difference between any two consecutive frequencies, let's say F5 and 7 here, what is it equal to? That is 7 times F7 minus F5, right? That is going to be 7 times fundamental. And this one is going to be 5 times fundamental. 7 minus 5, that is going to be 2 times fundamental. So finding the difference between any two, for example, consecutive frequencies here in a pipe that is closed at one end will always equal to 2 times the fundamental. And of course, we can use this to answer the next question. It says, there's a person that counts or measures 10 harmonics, Basha. Can the person find out like which harmonic are these belong to? Do they belong to a pipe that is open at both ends or closed at one end? By comparing the difference between any two consecutive frequencies, the answer would be yes. We'll say, if the person find the difference between any two consecutive frequency, if the frequency equal to 1 times fundamental, yeah, and it is equal to the fundamental, then the pipe must be open at both ends. But when the person finds the difference between any two consecutive frequencies, because obviously they have the data, right? If it is equal to 2 times the fundamental, then that must be a pipe that is closed at one end, we can say. So now let's get back to the question here, right? And this is the note that that I wanted to tell you here. All right, it says a student records the first 10 harmonic for a pipe. We don't know whether this pipe is open or closed. The question says, is it possible to determine whether the pipe is open or closed by comparing the difference in frequencies between the adjacent harmonics? Adjacent harmonics, that means the frequencies that are adjacent, come after next to one another, come after one another. With the fundamental frequency, by comparing that with the fundamental, the answer is yes. And the difference will be equal to the fundamental frequency if the pipe is open at both ends, and also the answer would be twice the fundamental if the pipe is open at one end. And of course, for this one here, we have also another question regarding this one. So let's solve this question, or take a look at this question too. All right, that is this question here. Basha says, the frequency between, or the frequency difference, that would be delta F, right? The frequency difference, that is delta F, between adjacent harmonics, all right, of a pipe, but if it is closed at one end here, right, what is it equal to? Good man, the delta frequency or change in frequency between adjacent frequencies for a pipe that is closed at one end, we just said that it is equal to 2 times the fundamental, right? For example, because these are only odd numbers, you can say F3 minus F1, right? That is always 2. Or we can say F7 minus 5, that is 2. F5 minus 3, that is 2. So always equal to 2 times fundamental. So it is equal to the fundamental frequency. No, that is for if it is open. Half of the fundamental, that is not. Right? Twice the fundamental, that is the correct answer. And then quarter the fundamental, that is not as well. And if you remember, since, like we started with this one, I would like to solve this question too. That is related to the previous question that, or perhaps the previous lesson that we were discussing. We have a question that says, how many nodes and antinodes are there in the fifth harmonic in a pipe that is closed at one end here? So if you remember the equation, Gutman, the number of harmonic here, it is equal to number of nodes and antinodes minus 1. Yeah? Here says the fifth harmonic, that would be F5, you can say, right? And then number of nodes and antinode minus 1 here. So now move the 1 to the other side, so we can say number of nodes. Now, so let's just write antinodes in a capital here. Number of nodes and antinodes, right? Number of nodes and antinodes, it is equal to 5 plus 1. That is going to be 6 here. So we have 6 nodes and antinodes here. So the question says what? It says 5 nodes and 5 antinodes, no. 4 nodes and 5 antinodes, no. 3 nodes and 3 antinodes. Watch this. These are a total of 6 nodes and antinodes. So how many nodes and how many antinodes? Is going to be 3 antinodes and 3, of course, nodes as well. So which one is correct now? 3 nodes and 3 antinodes. That'll be the correct answer, which is also a good question here. All right, now going back to the next question that we have, which is this. Says, what is the fundamental frequency of a 0.2 meter long organ pipe that is closed at one end when the speed of sound is this much? I believe these questions are pretty easy now. Right? You just know what situation you have. It says closed at one end, so know your equation, right? So we can say fundamental, they got N times V over 4L, right? So we have, says what is the fundamental? So that'll be 1, right? What is the speed of sound? That is 352. What is the length of this, the pipe? That is 0.2, right? So just do the math, you'll find the answer, which is 440. Pretty simple. Okay, next. Says a fluid is essentially a pipe that is open at both ends. The length of a fluid is approximately 66 centimeter. Convert that to meter. What are the first 3 harmonic of a flute when all the keys are closed, making the vibrating air coulomb approximately equal to the length of the flute? The speed of the flute is this much here. So, all right, let's just do this one too. Let's go back to the other one. Okay, so now the first, what are the, says, what was the question? What are the first 3 harmonic one, yeah? So let's find that one. You see the question too. Remember, it says, what are the first 3 harmonics? Yeah, since you know what it is, so just use the right equation, that'll be it, right? So, but don't forget, it says both ends open, right? So fundamental decata N times V over 2L. Okay, so F1, decata 1 times speed of sound in air, 340, divided by 2 times the length, convert that centimeter to meter, that'll be 0.66 meter. So you'll find the fundamental, which is 260 hertz. Basha, that is fundamental. What about the next one? 2 times fundamental. What about the third one? Right, 3 times fundamental, and that's it. So remember, fundamental is the key. If you know fundamental, you can find any other frequency you want. A vowel string, that is also, remember now, this is a string. So this is why very important to know what situation it is so that you can use the right equation for that. So we have a string, it says 50 centimeter long, that is 0.5 meter. That is the length, we can say. Basha says has a fundamental frequency. What is the speed of a sound? So this time, find the speed. One fundamental frequency, decata, 1 times V divided by 2L1, yeah? So we want the speed in here. So speed decata frequency times 2L. We have the fundamental, which is 440 times 2 times 0.5. Converting that to meter, you can find the speed of a wave, which is about the speed of sound in air, which is about 440 meter per second. That's it. Pretty easy. We have a different question this time. It says a flute is similar to a pipe that is open at both ends, while a clarinet, it is similar to a pipe that is closed at one end. Explain why the fundamental frequency of a flute, it is twice that of the clarinet. So your job is to explain why the frequency of a clarinet, it is twice than that of the fundamental frequency of a flute, right? It is twice that of a fundamental frequency of a clarinet, right? Even though the length of these 2 instruments is approximately the same. So even though they have the same length approximately, but why the frequency of one of them, it is equal to or sort of twice the frequency of the other one. Now, of course, the question says explain. There are 2 ways, or you can say, there are ways to answer this question for. First, let's begin with some of these questions right here. All right, so now regarding this one, when it comes to frequency and wavelength here, you can compare their wavelength here. So we can say, since they have the same length, all right, so we can say the wavelength for a flute, all right, it is equal to what? We're talking about the fundamental, right? Fundamental frequency here for flute here. It is equal to 2 times the length, right? That would be the length of a flute. What about the fundamental frequency for clarinet? Because it is considered as a pipe that is closed at one end. So we can say 4, right? 4 times the length in here. So how do you compare these lengths now? all right? Or if you want to write this as an equation here, you would say the wavelength for a clarinet, Basha, that is equal to over, let's make that a ratio, wavelength of a clarinet over wavelength of a flute decata, about 4 times the length, and this is 2 times the length, all right? So these are approximately the same, so you could simplify this. We can say the wavelength of a clarinet, it is about 2 times the wavelength of a flute, all right? The wavelength of a flute based on this equation, right? But you do know that frequency and wavelength are inversely proportional, yes or no? Frequency and wavelength are inversely proportional. Watch this. Now, according to this, the wavelength of a clarinet, it is greater than the wavelength of a flute. Now, what about the frequency? In this case, how many times bigger? 2 times, right? So now we can say the frequency of the clarinet now, the frequency, of a flute now must be 2 times greater than what? 2 times greater than the frequency of the clarinet here. Okay, because frequency and wavelength are inversely proportional. If the wavelength of clarinet is larger, so the wavelength of flute is less than this, all right, this is larger, the frequency of the flute must be larger than the frequency of the clarinet by factor of 2. That is one way to prove. There's another way. All right, we can use their fundamental frequencies. Fundamental frequency of a flute over fundamental frequency for a clarinet here. For flute, right, it is, what is it equal to? You could say clarinet doesn't matter here, right? It is equal to N V over 2L, and then the other one N V over 4L, right? So these are fundamental, V and V cancel out. So here, if you want to do that, fundamental frequency of a flute, it is over the clarinet, or flute over clarinet, decata. This one, of course, goes up. The length will also cancel out. That would be 4 over 2. We could just say 2 simply, right? So once you cross multiply, we can say fundamental frequency of a flute, it is 2 times the fundamental frequency of a clarinet here. That is how simple you could get this one here. So to answer this, we can say because in the flute, the first wavelength produces 2 times the length, while for clarinet, it is 4 times the length, which is this one right here, all right? The speed of a sound in both instruments is the same here. So according to this equation, the fundamental frequency of a flute must be twice of that of a clarinet here, right here. Right? That is one thing if you want. If not, you could, of course, use this explanation, which is pretty much the same thing here. All right, moving to the next question. All right, this question says the human ear canal is about this much centimeter. That is also another question, of course, that require your understanding here, or at least having some knowledge regarding the human ear. Oops. All right, let's go back to this. All right, says the human ear canal is about this much centimeter long and can be regarded as a tube, all right, open at one end and closed at the eardrum. What is the frequency around which we expect hearing to be best when the speed of sound is this much? All right, so by the way, whenever they ask you about the human ear canal or human ear, remember that is a pipe that is open, or considered as a pipe that is open at one end and closed at one end, Baba. Don't think about this, that you have an ear, like a canal here and an ear canal there, so that is considered a pipe open at both ends. No. Well, maybe it is true, actually, as a matter of fact, for those, for example, when they hear something and it's almost like a few seconds later, they act like as if they haven't heard it. Huh? Sometimes saying, like, for example, when people talk to you, it's almost like that it goes here and then gets out of the other way. We're not talking about these kind of human. We're talking about a human when sound goes there, and of course they listen. I don't know what next, because that's really whatever. All right, so the human ear canal is this much. So the question says, what is the frequency around which we sound here? So always find the fundamental, if that is the question. Fundamental decata, N times V over 2L or 4L. That would be 4L because this is for closed. All right, so as for this fundamental, that is 1 times V of speed of sound, 340, divided by 4 times the length. It is, remember that a centimeter, convert that to meter, so 0.028, right? That is going to be in meter. And then just do the math, whatever it is equal to. So what is that equal to now? It is equal to 3 or 30. That is going to be hertz. That is according to these numbers. That would be the best frequency, or the best frequency to hear. All right. All right, the next question that we have is this one. Also, this one you have to kind of like be aware of this one too. It says the fundamental frequency of an open organ pipe corresponds to the middle C, which is this much. The third harmonic, F3, of another organ pipe, but this one is closed at one end, has the same frequency. Now, I want you to underline this one for yourself. Compare the lengths of these two pipes. Because it says they have the same frequency, so these two are the same. So kata F1 for a pipe that is open at both ends, Basha, it is equal to F3 for a pipe that is closed at one end, Basha. So remember this too. I'll just write O for open and C for closed in here. These two are equal to one another, so compare their length. So for open, it is equal to what? 1 times, since it is fundamental, that is what the question says, times V divided by 2 times the length for the open one. All right, what about for third one here? Because remember, it says third one, so 3 times V, don't forget, divided by 4 times the length that is closed one here. So now V and V cancel out, of course. This one is nothing there. So now all you have to do, just compare these two. So 2 times 3, that is 6. Times the length of the open pipe, that is equal to 4 times the length that is closed at one end here. Now at this point you can simplify further. You could say by 2, that would be 2, and this is 3. So now at this point here, where the question comes from or becomes a little bit tricky. Because now that is the answer, comparing their length. But if the question says compare the length, for example, of the open compared to the closed one. So now at this point, let's just cut it short. At this point, whichever the question is asking for, make that the subject. For example, what if it says, what is the length of the open pipe compared to the closed one? So both sides divide by 3 in that case. So at this point, if it says find the length of a pipe that is open, the kata 2 over 3 times the length that is closed. What if the question says find the length of the pipe that is closed compared to the open? In that case, of course, is going to be what? 3 over 2 times the length that is open. So this is how you can find that. So pretty easy at this point, but of course you have to be aware of that. Now we have a few questions here. Some of them are important. Let's go through these real quick. It says, what is the longest wavelength? I got it, maybe. How with the longest wavelength? That is the fundamental. For a pipe that is closed at one end, that would be 4L. The fundamental frequency, pipe closed at this much, the frequency of the harmonic that comes directly after, if it is pipe, if it is open, you would say 2 times F. But if it is closed, the next one that comes after that is going to be 3. So 3 times 35 there, right? So the next one is going to be 3, which is 3 times F1. You could just find that since this is the fundamental. All right, after that comes after the fundamental, right? Remember this. All right, here question 3, that is also question 3 and 6 are interesting. Says an air column in a pipe vibrates at a fundamental pitch, which is this much. If the length of a pipe was doubled, the fundamental pitch would be what? That is an interesting question. I would love you, like or see you try this question before me solving this. That's not the button that we wanted. All right, this is what we want. Yalla day. Did you try? What is the answer that you got? Watch this. There are 2 methods to do this one here. I believe I'll start with the easiest one here. What is the relation between the frequency and the length? Right? Is it directly proportional or inversely proportional? Inverse, right? Very good. So now, if the length doubled, right? Or if the length was doubled, If the length is doubled, by what factor will the frequency change? Or can I just say the frequency reduces to half? Yes. So the frequency that I have is 680, right? So if you divide by 2 or make it half, what would it become? That would be 340, right? Which one is 340? That is A. That is one method to do that because frequency and length are inversely proportional. So if the length is doubled, frequency would be half. That's what it is. So that frequency, just make it half. That it doesn't matter if it is a pipe, even if they don't mention which pipe it is, because these are the same thing. But if it is a pipe that is open at both ends, n times v over 2l, right? If it is a pipe that is closed at one end, that is also n times v over 4l. But what is the relation between frequency and the length here? We don't care about these numbers here. Isn't that inversely proportional? That is one thing. Now, regarding the second method here, all right, so because if the length is doubled, yani frequency kish, the beta half will reduce to half here. Now, if you use the equation here, right, whichever the equation it is, all right, once you double the length, all right, so whatever the frequency that you get, just divide by 2. Here, divide by 2. In this case, it is going to be the same thing, or whatever the frequency that you got previously, now you just divide by 2, which is the same thing now. 680 divided by 2, that is going to be 340, which is the same thing that we have. But I prefer this method because it is easier, right? Because the relation between frequency and wavelength, it is inversely proportional. My bad, frequency and the length. All right, question 4 says, what is the third harmonic? This much is, these are easy. Speed of sound, dosh, asana. Question number 6, all right? Once again, I would love to see you try this question before me solving. So if you're watching this, you may pause the video and give it a try. Be confident. It says a harmonic wave is traveling, along a pipe or along a rope. The period of the wave is, so a harmonic wave, we can say, we have a wave, is traveling along a rope here. Okay. The period of a wave is 0.8 second. So if you start at one point here, the period, that would be the time for one oscillation, right? It is 0.8 seconds. So we can say 0.4, that would be half a period. This is 0.8 second for one period. All right, we don't need the diagram, but I'll just did that. It might be useful for some other questions. So the period is 0.8 second. Says the wavelength, it is of this wave, the wavelength, it is 0.2 meter. All right, so that is one thing. The question says, what distance is traveled? What distance is traveled by a given crest? Asha, how far a crest can go? All right, of the wave or of this wave along the rope in a time interval which is equal to 12 seconds. So how far a crest can go in a time that is equal to 12 seconds here. How far does it go here? When it says how far does it go, that is delta x, don't forget. But now think about this one here. If you have the period and the wavelength, what can you use, or since you have a wavelength, right, what is the use of period unless you find the frequency? Got the frequency, the 1 over the period, that is 1 over 0.8, that is going to be 1.2, I guess. Let's double check. 1 over 8. 0.8, my bad. 1 divided by 0.8. The answer is 1.25. 1.25 hertz. That is the frequency. Basha, if you have the frequency and the wavelength, what can you find? Can you find the wave speed? Yes. So wave speed, the frequency times the wavelength. Frequency is 1.25. The wavelength, the question gives it to you, which is 2, right? So what is that equal to now? That is going to be 0.25. Now, remember to find the distance, use the regular equation here. So we will say delta V, or V, it is equal to delta X divided by delta time. Why is that? Because now we have speed. The question says, how far does it travel? All right, and in this much time here. So how far, that would be delta X, don't forget. So now all you have to do is cross multiplication, right? That would be delta X, it is equal to V times delta T here. The speed of the wave, it is 0.25 don't forget this meter per second. Okay, 0.25 times the time, which is 12 seconds. Once you multiply this, of course, you will get what is 0.12 times 0.25 times 12? 0.25 times 12, the answer is going to be 3. So the answer it is going to be 3 meters now. This is how far the wave will travel in 12 seconds, which I pretty actually say this as a good question here, because now you have to do many steps in order to get to this one. You'll have to use 1 over period to find the frequency. Once you find the frequency, find the speed of the wave, how fast it is traveling. Then if this is how fast it is traveling, how far can it go in 12 seconds? That is going to be 3 meters here, which is a pretty good question actually. All right, now let's talk about another concept, and that is harmonic accounts for a sound quality or timbre. What is exactly this thing here? All right, now remember this. If you look at this table here, or something before that, this table shows harmonic present in a tuning fork. We have a tuning fork and we have a clarinet. If you look at the table here, what do we have? These are the number of harmonics and these are the relative intensity. And this is the sound wave that is produced. When a tuning fork is struck, Basha, it produces a certain sound. It goes like ting, right? This is what it is. So it has a, we can see that, it has a certain or one harmonic, even though if it is struck way harder, it might give, like different harmonics. But at this point here, we only have one harmonic. And if we draw a sine wave for the wave that is produced by a tuning fork, this is how it looks like. It is a simple or normal sine wave right here. Why? Because we have a simple harmonic here. But for a clarinet here, for example, once a clarinet is played, for example, with a certain frequency, you can see that we have, or once played, let's say, we have different harmonics, and each one of these harmonics have different intensities, as you can see here, because this is harmonic and this is the intensity of each one of these. You can see that some of them are higher than the other one. The bottom of this, for a tuning fork, we have a certain or one harmonic, but for a clarinet, once it's placed, we have a bunch of harmonics together. As these harmonics are combined together, then it produces one final sound. All right, and this is the sound that we hear. But if you look at the sine wave of this harmonic compared to the, or the clarinet compared to the tuning fork, even though they're playing the same note, right, you can see that these are much different from one another. It is true that these are both sine waves, as you can tell here, crust and trough and crust here, trough and crust in there as well. But you can see that all these up and downs here, these are a mixture of harmonics together. Or we can say when these harmonics are combined together, then, and this would be the reason why the sound of a clarinet would be much different than the sound of a tuning fork. Now, let me ask you something else. Have you ever wondered why no two musical instruments ever sound the same? That is because they have different harmonics, and as these harmonics are combined together, of course, different harmonics and also at different intensities. Once these are combined together, then they produce a distinctive, a specific sound wave that is only for that instrument. That's why they sound different. For example, the sound of a guitar is different than the sound of a piano. Sound of a piano is different than the sound of a, let's say, of a flute, of a clarinet, of a saxophone, for example. So each one of these are sounding different, even if they play notes of the same sound, right? So this is the reason why. Okay, so regarding this, we can go back to this. We can say harmonics account for sound quality or timbre. So having these distinctive sound is what is called timbre, which is a result of the combination of these harmonics of different intensities. We can say that. Now we have only two definitions, and these two definitions both are bin and wizari, right? All right. So the first one says timbre, which is a musical quality. So whenever you hear or see the word musical quality, that is a timbre. So whenever you see the musical quality, of course, that is timbre. So this is a keyword and need you to underline them here. Another thing that we have says, from that, of course, sound of a tone resulting from the combination of harmonics. So whenever you also see the combination of harmonic present, that is also a timbre. So the second definition that would be, it is a mixture of harmonics that is that produces the characteristic sound of an instrument. These are we can say timbre here. So remember, we have timbre, that would be the musical quality, or musical quality would be a timbre, and of course, or you can say timbre, it is the combination of harmonics here. Now, a few questions regarding this one says, what does the timbre depends on? It depends on the number of harmonics and their intensities, don't forget. What about the Gutman, just like the diagram you saw, the table over there, for the tuning fork it was one harmonic. Of course, it was certain intensity, but for the clarinet, there were different harmonics at different intensities. So this is why they sound different, or this is what timbre depends on, both the number of harmonic and their intensities as well. Why does a clarinet sound different from a tuning fork? It could be, why does a guitar sounds different from a piano? Why does it could be any musical instrument sounds different from another musical instrument? That is because even when these, because of their differences in timbre, even when they play notes of the same frequency, they have different harmonics, a different intensity. The combination of these harmonics, of course, lead to a different timbre, right? And also the intensity of each harmonic varies with a particular instrument, like we said, depending on the frequency, the amplitude of the vibration, and the variety of other factors. The last thing that we have is fundamental frequency determines pitch. All the points that are here, most of them are repeated, but there are one or two keywords that needed to be aware, or need to introduce them to you. The frequency of a sound determines pitch. That is nothing much. In musical instrument, the fundamental frequency of a vibration typically determines pitch. That is also nothing new. Other harmonics are sometimes referred to as overtone. That is also not new. Previously, we were talking about overtones, good man. If we have the fundamental frequency, right, when the frequency is doubled, for example, let's say for a string here, right, F2 the kata, 2 times the fundamental one, yeah? Kata, those are twice of this, you can call them overtones, all right? What about F3? The kata 3 times F1, that is also another overtone. But now we're gonna call this one first overtone, and we're gonna call the one that comes after second overtone, third overtone, and goes on and on. The next thing is this much. It says, or this one here says, in a musical scale, all right, or in the harmonic half step or musical scale, there are 12 notes. I need you to know this one, each of which has a characteristic frequency. So we have 12 notes, Rasha. Each one of these notes have a different frequency, and these are the notes that we have. And if you start, for example, from this piano keyboard in here, or keys, between A to G, there are 12 notes here. I mean, not G here, this one here. There are 12 notes. When it comes back to A, that is going to be the 13th note, and you can start counting here. 1, 2, 3, 4, 5, 6, 7, 8, and then 9, 10, 11, and 12, all right? Now, the 13th note here, it is going to have twice as much frequency as the first one right here. So, for example, the frequency of this note A, it is 220. The frequency of the 13th note, that is another A, but is going to have twice as much frequency here. So now you can call this one, of course, you can call this one an overtone because the frequency is doubled. But if there is also another key, actually, I want you to know that. Now we can say that these two keys are 1 octave apart, Basha. So one what? 1 octave apart. So 1 octave apart. So whenever the frequency doubles, that is 1 octave apart. What if, for example, what if I have another key here, the one that is another octave there, that is going to be, or twice as this one, so this 440. So the next one that is doubled, that is going to be 880 hertz one, yeah? So this 440 and 880, this is going to be another 1 octave apart. But now, starting from this one, for this one, that is going to be 2 octave apart from this one. Maybe nothing that much, but I just wanted you to know. We said the frequency of the 13th note, it is twice of the first one, which is basically 13th note constitute of 1 octave above, you can say, or apart. That is the same thing. All right, now, these questions, it says the timbre that produces or produced by a mixture of harmonic. We said whenever it says a timbre that is produced by that is sound quality. And then this question says it is the musical quality. We said whenever you see musical quality, that is a timbre of a tone resulting from the combination of harmonic presented at a different intensity. That'll be the timbre. You can see that it's been in Uzari so many times as well. And this is nothing new. This is from the previous question. Man, if F3 and third harmonic is this much, what is the second harmonic for a pipe that is open at both ends? First find the fundamental, then finding the second harmonic becomes easy. Now, this is nothing much in here. These questions are pretty much easy, right? If a piano in item 1 is this much, what is the speed of a sound? These are nothing new here. Question 3 says, in a clarinet, the reed end of this instrument acts as a node, and the first open hole acts as an antinode. While the clarinet is considered as a pipe, close that one, and you need to underline this for yourself. What harmonic series is predominant, right? Or what harmonic series is available in a clarinet? We can say only the odd harmonic because it is considered as a pipe that is closed at one end. All right, this critical question, right, says which of the following are different for a clarinet, and of course could be a saxophone. By the way, we have 2 other different names in the book, but I've changed them here. As long as one of these, all right, one of these considered as a pipe that is open at both ends here. So for clarinet, close at one end here. That is as long as one of them, right, closed at one end, and then the other one is open at both ends. Basha, open at both ends, or it could be a string instrument. Doesn't matter, right? So that is what we have. One of them is closed at one end, and the other one, it could be open at both ends, or it could be a string. Or it could be a string here. Okay, so we have a banjo, and I think there's another name there. All right, so anyway, but like I said, as long as one of these is open at both end or string, or the other one is closed out, it'll be fine. So whatever the name is, that'll be totally fine. So, and the other one is a saxophone here, open at both ends considered, right? When both play notes of the same fundamental or at the same fundamental frequency. I need you to know this one here as well. When it says play notes of the same fundamental, that means they both have the same frequency. So we can say the frequency of the one that is closed that is equal to the frequency of the one that is open at both ends, or it could be the string here. That is what it means when both have the same fundamental frequency there. Now the question says, so which one of these would be different here? Now the first one says the wavelength in the air. Bash, if they have the same frequency, well, the wavelength will be different. No, even the wavelength will be the same. So the wavelength is going to be the same. What about which harmonic are present? Yes, that'll be different because now we said, remember the tuning fork and the clarinet one, yeah? On each one of these, of course, have different intensities and also different harmonics at different intensities. So each one of these would have different harmonic, all right? Different harmonic. The reason why, because for the one that is closed here, good man, the harmonic is going to be N, is going to be 1, 3, 5, 7, and so forth. One, yeah? But the one that is open here, the harmonic is going to be 1, 2, 3, 4, and so forth. Got that? The harmonics will be different. That is one of them. Next says the intensity of each harmonic. Now, going back to this, of course, if they have different harmonic, the intensity of each harmonic will be different too. So that just like the same for the tuning fork and the clarinet, you saw different harmonic, a different intensity, which you saw over there. All right, what about the speed of sound in here? Since it is the same medium, so it's not going to change. So the answer is now both B and C. All right, now these are a few extra Wuzadi questions. So these are nothing much, very easy ones actually. I want you to take a look at them and then solve as much as you can. But the first one that we have says, which of the following are different for a trumpet and a banjo, Basha? So we can say banjo, that would be a string instrument here. When both play notes of the same fundamental frequency here. Only the wavelength, all right, if they have the same frequency, the wavelength will be the same. Only which harmonic are present. So which harmonic is present would be correct. Only the intensity of each harmonic. So the intensity would also be correct. That we can say both B and C would be correct at this case here. What is the fundamental frequency of this much organ pipe, whatever? These are easy, nothing much or nothing new here. These are similar questions. What about, for example, question 5 and 6? 5, this is previously we've mentioned a question like this. And if the sound or decibel level increase from 30 to 60, by what factor will the intensity increase? Good man, 10 to the power 3 or 1,000 times. How? Good man, from 30 to 40, right? From 40 to 50, from 50 to 60. When every time increases 10 units, it increases by 10 times, right? another 10 times, another 10 times. That is a total of, we can say 1,000 times. We don't add them, we multiply them. So 1,000 times increase, and that is 10 to the power 3. What about question 6? It says, which of the following statement is correct? Frequency determines pitch. Oh, that is true. Pitch of a sound decreases as the frequency of a sound increases. No, that is quite opposite. Pitch is a measure of how high or low a sound is perceived. That is also true. Got that? Both A and C is correct, which is going to be option D here. All right, we're almost done. Now we have chapter summary. Take a look. I mean, you read them, of course. There's nothing bad in here. Of course, if it is not going to be advantages or whatever, at least it's not going to harm. Now, the first thing that we have says, when a part of sound wave travel, that's standardized test preparation, says, when a part of sound travels from air into water, which property of the wave remains unchanged? Basha, when it goes from air to water, of course the speed changes because the medium is changed. What about the frequency? The frequency will never change, right? The wavelength, if the speed changes, the wavelength will change too. Right, so not this. What about the amplitude? Also, that won't change because part of the energy would be transferred into the medium, so the amplitude will also be less. Now, regarding this question here, this is a pretty easy question here, but there is one thing I need you to be careful. A lot of students, they just start counting, for example, this black strips in here or this white one here. Right, that is true, sort of. All right, but what if the question is not exactly this? You might get it wrong, so be careful. All right, so they might just start counting here. For example, 1, 2, or you can continue or count the white one. 1, 2, 3. They say 4 wavelength one, yeah. What is the length of the whole thing? The question tells you that the whole thing is 1 meter. Actually, you have 4 wavelength equal to 1. Got the wavelength, they got the 1 over 4, which is equal to 0.25. And that is pretty fine here up to this point. But it is not fine if the question is not 4 complete wavelength. What if there is half, for example, a wavelength extra? How do we know if it is a 4 complete wavelength or not? You have to count every, for example, parts or every line that is here. So how do you do that? Starting from this black one here, there's 2 ahead, 1 to the next black one, 2 ahead. That is, so now starting from this to this point here, that is 1 full wavelength, right? So start a point, right? And then to the same exact point, that would be 1 full wavelength, even if it is not the center of a compression or rarefaction. These are supposed to be compression because very dark, assuming there are a lot of air particles or particles. These are bright, less air particle. That's nothing much, all right? So starting from this, like 2 ahead of the black, this distance to the same point, that is 1 full wavelength. That is 1. Now this is to this point here, that is 2. To this point, that is 3. And then to this point, that is going to be 4 complete wavelength here, right? If this is how you're supposed to count them, what if there are, for example, more wavelength in this case? You can start counting here, starting from 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, all right? Then up to this, that would be 10 lines, 10 strips, that is 1 full wavelength. What if you had, for example, 5 more lines in here? In that case, of course, it would have been 4.5 wavelength, the kata 1, then of course the answer would have changed. So be aware of that, make sure you count the whole thing. All right, the next thing is easy. If a sound to be getting louder, again, all right, which of the following is probably increasing? It means speed of sound, no. Frequency, no. Wavelength, no. Intensity, yes. And this one also here says, if the intensity of a sound increases 1,000 times, what is this increase equal to in decibels? That's the reverse of what we had before. So this time, intensity increases 1,000 times. We don't know from what intensity to what, but we know that increases 1,000 times. Kata, we can say I2 over I1, it is 1,000 times. Yeah? I2 increases 1,000 times compared to what we had there. You can write this as a fraction here. So the change in decibel level now, it is equal to 10 log of, instead of writing I2 over I1, we'll just write 1,000 instead, because this is how much it increased here. So write 1,000 as a power, that would be 3. Then use a calculator, you will see that it is equal to what? It is equal to 30 decibel, and that would be the change in sound intensity level relative sound intensity level, decibel, whatever you call that, that is perfectly fine. So the answer is going to be option C there. All right, Doppler effect occurs in all but which of the following? Or but which of the following situation here? But which of the following? So, of course, if your English is good, that is great. But if not, take a look at this map. It says Doppler effect occurs in all of these but zigala, right? So here, the word but, it means ziga, for example, or except, right? So except which of the following? It happens in all the following except then one of them, right? A source of sound, good man, as long as there is a relative motion, it occurs. If there's no relative motion, no Doppler effect. A source of sound moves toward a listener, it happens. A listener moves toward, that is also true. A listener and a source of sound remain at rest. With respect to another, that means there's no relative motion, so it does not occur here. A listener and a source sound move toward one another or away, that also occurs, so the correct answer is option C. If the distance from a point source of a sound is tripled, by what factor will the intensity of a sound change? Previously, we've mentioned that. Now, the relation between intensity and the distance, it is inversely proportional. So we said this is the equation. Whichever is unknown, make that one the subject, and you can find that. So if the distance is triple, that is 3, triple yani 3. So 3 squared, right, that is going to be 1 over 9. So the intensity decreases by a factor of, or changes by a factor of 1 over 9. Basha, what if the things were changed? For example, what if they were asking for the radius? Let's say the intensity changes, and then by this much find the radius. Then you could have done this one, r squared, then make r the subject. That would be 1 over intensity. All right, and then take the square root for both sides. We can say r, where the distance, it is inversely proportional with the square root of the intensity. So whatever the intensity is changing, you can plug that into the equation, and then you can find it. Why a dog? Why can a dog hear a sound produced by a dog whistle, but its owner cannot? There's, for example, there's this thing that produces, or the whistleblower here, right? Especially for dog owners, or if you want to avoid, or if you want dogs to avoid you, you blow the whistle, of course, and then it produces sound. We don't hear that, all right? But the dogs can be hurt or bothered by that. So why the owner cannot hear? Dogs detect sounds of less intensity than human. That is not true. Dogs detect sounds of higher frequency than human do. That is correct. Dogs detect sounds of lower frequency. No, dog detects of sounds of higher speed, not speed, because the speed is the same in the same medium. The greatest value ever achieved for sound, whatever, these are nothing much, right? You can do them yourself. This one here says the horn of a parked ambulance automobile is struck, or stuck actually. Sometimes, for example, if you try to open the door of a car that is locked, all right, so the horn will go off and then sounds. If the horn, if the horn is stuck, for example, goes like beep, whatever, right? So you're passing by that, right? You're in a vehicle that passes the automobile as shown below. So what is the nature of the sound that you hear? At this point, you're very far. As you passing by, your distance increases more and more. So you're approaching, you're getting closer to the source, and then after that, you'll be moving away from the source. So what happens as you approach the source? Of course, the frequency you hear, right, is going to be higher, but as you move away, it is going to be lower. So the frequency you hear is getting higher, and then it is, after you, for example, move away, it is going to get lower. So what will happen? The original frequency of a sound of a horn rises in pitch, right? Does it just rise? No. The original sound of a frequency drops in pitch. Does it just drop? No. A lower pitch is here rising to higher pitch? No, right? Because it is exactly opposite. A higher pitch is here because you're approaching, and then as you move away, then this pitch, of course, is going to be dropped. This is what you will hear. This is also nothing new regarding this one. This is also easy. Question 12, I would like to solve this one for you. Says the figure below shows a string vibrating in the 60th harmonic. The length of the string is 1 meter. What is the wavelength of the wave on the string? Now we've learned that, right? Because it is a string, so the wavelength here, the wavelength of any harmonic, for a string, 2 times length divided by the number of harmonic. Here we have 2 times the length is 2 meter, right? No, 1 meter. right, divided by the 6th harmonic. So divide by 6. That is equal to 2 over 6, which is 0.333 meter. We can say that would be the wavelength of the 6th harmonic here. 0.3 now, 3 meter, we can say. Basha, what if the question did not say the 6th harmonic? Just in the figure below. How would you find that? Well, we said that to know how many harmonic, you can just measure the number of loops. That would be 1, 2, 3, 4, 5, 6, right? That is one thing. Maybe next time they'll erase 2, right? And they say, for example, in this figure, without telling you this is the 4th harmonic. So you either measure the number of loops, right? That is 4 loop, or you could do exactly what he did in chapter 3, just count the number of antinodes here. That would be the number of harmonic. Whichever the method you do, that would be perfectly fine. There's another question here. It asks you to find the intensity, which is nothing much at this point. This question also, let me give you an idea. It says use the following to solve this question. The area of a typical eardrum is approximately this much. That is the area. The question says, what is the sound power induced on the eardrum at the threshold of pain? What if they don't tell you threshold of pain is this much? So threshold of pain, you need to know that it is 1 watt per meter squared, right? So how do you find the power now? We know that intensity dakata, power over area, right? So if you want to find power, dakata intensity times area. Intensity at threshold of pain, that is just 1 times 10 to the power 0, or just 1. The area here, it is 5 times 10 to the power negative 5. So you just do the math, you'll find the power in watts, and that'll be it. The next question says, what is the sound power incident on the eardrum at the threshold of hearing, right? So what if they don't give you, for example, what is the sound intensity at threshold of hearing? So once again, power dakata intensity times the area. We have the same area, but the intensity will change. That'll be 1 times 10 to the power negative 12. That is threshold of hearing, times the same area, which is 5 times 10 to the power negative 5. Do the math, you'll find the power in watt, and that'll be it for this question too. All right. Pipe that is open at both ends has a fundamental. These are nothing much. These are nothing new here. I would recommend you solve all these questions on your own here. The next thing that you have to do is pass Wizari questions, because some of these are very easy. Of course, once you solve these questions, of course, you will get a boost of confidence here. Of course, that encourages you to do more, and also you will get used to all the Wizari style or exam questions, which once you go to Wizari, nothing becomes new. So I would recommend you get a question bank or whatever, and then try to practice as many Wizari questions as you can, and you will see how beneficial that will be. All right, that'll be the end for this session, inshallah. Next time we will start with chapter 5. Till then, keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.